Okay, well, this week we're looking at a paper about unit vector representation, talking about different efficient versions of it. That's from 2014, so it's a bit older. God, 2014 is technically 10 years ago. I'll try not to think about it too much. Okay, so what's the abstract? Um, Bandwidth is a limiting factor. Yes. Okay, so different ways of non-register unit vectors. Not sure what that means. Not sure. Okay, I do get the statistically independent unit vectors. There's, each unit vector is independent from its neighbors.
Yeah, I'm trying to think. I don't know. You would think it would be in register. That's what you want, to get a faster cache. It's the opposite.
It just means in register, then this is probably not the best representation because in register means you probably want to manipulate them. But so this is a storage format, basically.
Yeah. This is trying to make your loads and reads and the loads and stores as small as possible. But once you get them into your register, you want them to be, or this is not talking about trying to make your register usage smaller because you might have X number of 32-bit registers, but that's cheap to do computation on. What's expensive is filling those 32-bit registers with data. And if you can get away with, I don't know, 10 or 12 bits, then that's gonna help your bandwidth massively, is what I'm understanding from the abstract. Just a quick look through it. So we got 16-bit octahedral P encoding, 24-bit SNORM, 24-bit octahedral in RGB8. I mean, it's progressively more detailed, and you can see the um, pixelation in the mirror finish and glossy here too, whereas over here it looks reasonably smooth on the right.
So octahedron is better than SNORM, and more bit is better.
Yeah. Okay, let's go into the article. Unit vectors everywhere. Yeah, bandwidth for stuff like a G buffer, but many other reasons to be concerned about bandwidth beyond just the G buffer today. That's kind of impressive.
Yeah. For positions, how
Yeah. It's not depth though, from what I'm reading. Then again, position might actually include depth. So never mind. Okay, so this is making a distinction. The registers are high bandwidth, medium bandwidth RAM chips, and caches, and then low bandwidth storage for disks and network data, network access. A high bandwidth use case, you want to minimize your decode time, but your low bandwidth case, you want to minimize your storage space, which is kind of an opposite, an opposite problem. Yeah, for a unit vector. Wait. Oh yeah, three 32-bit floating point numbers. Yeah, that'd be 96. I'm just 96 bits is an odd thought to have because I'm used to seeing bytes, and that's what 24 bytes. Yeah, that's 24 bytes, isn't it? I think.
Oh, yeah.
I think it's 12 bytes, right?
Oh, that makes more sense. 12 times 8, that makes more sense. Okay. Yeah, I'm just used to seeing 20 bytes instead of bits, so the 96 threw me off.
Yeah, that in my mind that is a big number, but it's actually just 3 floats.
Yeah, but it is that many bits, so we're not going to be talking about low bandwidth stuff here because that's not what we're dealing with. We want the medium bandwidth stuff. Yeah. You want a trade-off between space and time efficiency, more space efficiency, but not at the cost of too much time spent decoding and encoding, but you can introduce a significant error. So that is the confines of it. So compressed textures use statistical dependence of spatially local surface normals to reduce storage needs. And it's like, if you aren't using compressed textures, just go do that right now, because that's going to be a more important thing than getting whatever the formats this paper talks about. You can do both, but just using compressed textures is an easy win. Oh, okay. But if they don't have statistical dependence, then we want to survey those methods. Hmm. Okay. So let's formally describe the problem. Unit vector representation used fused bits with acceptable error, or minimize error for fixed bit width. So our baseline is gonna be, our straightforward representation is 96 bits for a vector. If we use floating point numbers, most of the numbers are completely useless because they don't encode numbers inside the unit sphere. So your 96 bits, you get like, I don't know, I'm not gonna put a number, but very few of your bits are actually going towards the unit vector. And everything else is just zeros or ones or non-useful bits. Yeah. Every possible bit pattern to represent a unique point on the sphere. Yeah, because a naive, 32-bit float, 3 floats, anytime one of the floats is larger than 1 or smaller than 1, all of the other 2 floats values don't matter because you're representing a number that doesn't lie on the unit sphere. So, okay.
It's matters is the like the length is the like 3 numbers combined, right? You can't decide it independently.
Right. I shouldn't say what I said, but I think I was more thinking just out loud about how the it's a very no, you aren't storing a unit vector when you're using 3 floats. You are just storing a vector, of which sometimes it can store a unit vector if you decide to do so. So if we just use two 32-bit floating point or fixed point angles for a unit vector, we get, 64 bits per vector, and we get even better precision because more of those bits, the bits are always going to be used for representing a unit vector. But because they require trig to convert back to Cartesian product, they aren't free. Well, they
They're
also
very
introduce,
expensive.
yeah, they are. Yeah. And they also add some error in the whenever you do those computations. Hmm. Yeah. If you were to map out all of the locations, a 64-bit spherical coordinate of 2 angles, most of them would point towards the poles if you were to equally divide it amongst the sphere, latitude, longitude kind of thing. Although that's not 2 angles, that's, never mind. Okay. Hmm. Yeah, in many cases, when we have unit vectors, we actually have hemisphere vectors, but because we often do need a unit vector for other things, it's not really worth focusing on the hemisphere case over just an efficient unit vector. So we're always to encode, we're always taking 3 floats and turning them into a compressed form, and then when we're decoding it, i.e. loading it. So encoding would be saving it to a buffer, saving it from a register to your medium bandwidth storage, and decoding it or loading it from that representation into 3 floats. I mean, that's always a fun trip when float 32, you realize a float is actually just an approximation of a number to begin with. A decent approximation, but still an approximation nonetheless. Well,
Yeah, float is not a real number. It's a subset of rational number. People always say that.
yeah, the other way I've heard it described is it's every floating point number, quote unquote, is actually a range of values. So if you have, especially at the very high end, you know, you have exponents that are very large, and the mantissa gets larger and larger, it becomes clear that the, you know, each floating point value represents all numbers within a range. Because there just aren't any, there isn't enough precision to store any number smaller than that, or any numbers with the more precision. Now, okay, that's redundant. Anyways, well, so they're gonna have some exotic formats that don't like exist, but that's fine because we can just pack the bits arbitrarily. That'd be interesting. Follow-up paper is comparing current hardware design and its integer versus floating point capabilities, since this is a 10-year-old paper. And if you look at the modern APIs, Metal, Vulkan, DirectX 12, they all started appearing at around this time or later. So new hardware of this day would have been their baseline hardware for the most part. And almost all the new hardware coming out in 2014 has since gone out of support. Oof. Okay, uint b, unsigned integer with b bits on the range 0 to 2 to the b minus 1. Fix I, fixed point representation of unsigned integer scaled by a constant negative power of 2 that represents uniformly distributed values on this range. So we don't use fixed point anywhere because it can't represent 1 without wasting an entire bit. That's kind of lame, but understandable. Float b is floating point with b bits total, where float 32 and 64 are well known, but float 16 exists, and I think float 8 might exist, but I don't really know, and I can't imagine what you'd use float 8 for. So unorm, unsigned normalized fixed point, represents 0 to 1 with exact representation of both endpoints. This is a pretty common thing to do. It's pretty much what you want for a unit vector type thing, where you want to you have a number between 0 and 1, and you want to space your bits equally over the range instead of floating points non-linear distribution of representations. Scaled and biased unorms. So their S norm is usually scaled and biased. It's a long way to say S norm, but I guess this also applies for arbitrary range if you really wanted to.
Only used in legacy systems, so you can ignore that.
Oh, okay. I didn't see S norm down here. Yeah. Yeah, legacy. Okay. Okay. Finally getting to the representations. Um, renormalizing the vector using at least float 32 precision after decoding. Oh, vector floating point normalization. Is that what it's? Oh no, it's talking about normalizing the vector to ensure that it's actually a unit vector. Right?
Yeah,
Yeah. Because it's even if it's not a unit vector, it's still pointing in the right direction. However, some math might not like it if it's not a unit vector proper, or it might just be less precise over time.
Or
do
yeah, the representation could be less precise than just having 3 float 32s.
mm,
So if you decode and it's like, you know, not a unit vector, just due to the fact that it's less precision, they have to renormalize.
yeah. Okay, that explains that. And of course, they're not really talking about it. They're just like, we're not going to be talking about it. So, okay, float x3 discussed before. S norm 3, use S norm for each axis. That already increases the precision and probably is the most precise format shown here. No, like maybe not, because there's still going to be lots of values that are not unit vectors in the S norm space. But it's better than float x3. Spherical coordinates, 2 angles, theta and phi. Oh. Okay, that's a fun quirk.
Is it still true now?
I mean, I don't see any hardware, I don't see any texture formats that have a SNorm / UNorm capability. It's all UNorms or all S norms. But like, I don't know. I really don't. But of course, spherical coordinates are not the best distributed, as mentioned before. So there's still representation error. And they require trig, so that's expensive. Project onto a cube. Then store the cube face index and coordinates with it. It's hard to work with and has high error. And the error accumulates near the vertices. And you have to use 3 bits to specify which face the rest of the coordinates therefore. Wrapped cube. Okay, so it's a cube, but you distribute the representation points, you skew them. But they have cost of trigonometry, which is no good for performance. And if you just went with the octahedron, you would have had a better time anyway. Oh, this is an interesting idea. You just label each section as a, index. I assume there's like 64 of them. So you have a byte of that at least. That long. Divided into approximately equal areas. Optimal spherical coordinates. Yeah, and this is not latitude, longitude, which is more akin to spherical coordinates. Lowest error of all surveyed, but the height encode and decode is not awesome either. So map the sphere into an octahedron, project down the z=0 plane, and reflect the negative z hemisphere over the appropriate diagonal, as shown in the next figure. The result fills the -1 + 1 square. So store the UV coordinate in the square as SNorm2. Oh. Yeah, where you divide the sphere into 8 quadrants. No, that's not how quadrants work. There's only 4 if there's quadrants. I guess you map the octants. And so if you are in the negative z plane, then you're gonna flip the coordinate into the blue region here. But if you're not, you're in the red region. So you have a square of which everything is more or less evenly distributed, or at least much more so than the cube distribution. And it's easy to do performance-wise. It maps the sphere to the octahedron by changing the definition of distance from the L2 norm to the L1 norm. Oh. So the first paper had bugs and that's been fixed. So yay. Oh, stereographic equal area and equidistant, some cartographic inspiration for mapping hemisphere to a unit radius disk. Okay, so the Meyer paper, which has been referenced multiple times already, does some surveying, but we do more in this paper. Minimal and maximal error, demonstrations, measuring encode and decode performance, okay, and providing a lot of things. Interesting, okay. So the different encoding patterns can then be subdivided into bit length variants, where we parameterize by the total bit size of the output. You know, octahedral 24 has 12x2 parameterization onto the unit square. Oct 16 is S norm 8/2. And most of the representations, except for the naive ones, use 2 parameters, which get a equal bit width. I like the omission that some formats using sign bits and set other various things don't fit well to the descriptive text and just look at the supplemental code. An equation trying to handle positive or negative bits is not the most elegant thing, generally. Okay. Oh, so there's the mapping of S3 to, where was it? Oh. Oh, sphere, the real sphere to R2 is lossy, and then the R2 to Z2 mapping is also lossy, but can be a biased loss of air of precision, which happens because of the rounding down of integer arithmetic. Uh, yeah, some representations just suck, and we're not going to spend too much time worrying about it. Um, Yeah, the lat long is cool for its having a table, but that just does mean you have to do a decoding in a different fashion than other formats. Because you pretty much need a lookup table to do it efficiently. Oh, that's a fun observation. You just take your integer value and treat it as an index into a table for the actual value. Totally doable, but it's completely bonkers from a I want to minimize bandwidth perspective. Oh. Okay.
Is it like the index sort?
I don't know if it's sorting person. Yes, kinda. I mean, if index sort is what I think it is, index sort.
And
I
just
don't
trade space for time. Like,
Yeah, if your number range is is like the, yeah, I think you're right. It's the same concept. But instead of sorting numbers, it's just doing lookup and decoding. You basically store out every, possible integer or a floating point value for each integer input you have.
Yeah.
But yeah. I guess if you don't worry about bandwidth because you're working in 1997, then I guess that makes sense, but you don't live in that world, unfortunately, at least not anymore. Oh yeah, you could put that into a cube map and just sample the cube map. But you'd have to have a pretty big cube map. And again, bandwidth. So you got some reference implementations. Uh, and then for CPU and OpenGL, so GLSL, which should still be usable in other contexts that aren't only OpenGL, but hey, it's fine. So here's the octahedral, the fast encoding for octahedral. Just a basic sign check for X and Y. Would a compiler optimize the ternaries into something different? Like, what would a ternary be optimized into other than a branch? I'm trying to think if there's some math expression that GPUs
Well,
can do.
they're fundamentally just an if statement,
Yeah,
so they optimize the same way, most likely, unless the compiler has heuristics to you know, optimize them differently.
I mean,
which, uh,
I guess I'm just
At
thinking,
least for CPUs has some specific instructions to avoid like hard branch, but for GPUs, I don't know.
I guess I was more thinking about the fact that its outputs are 1 and -1. And if it was just like, if you could do some math to get the same thing, but there's a lot of ways to get that and they all are effectively a switch. Ooh, ternary operator for SEL assembly, that's fun.
yeah, AMD ISAs have select as well. So
Oh. Cell select, yeah, that makes more sense. Okay, assume it's normalized, project onto the octahedron. And then onto the plane. So we have the XY coordinate, we multiply it by 1 over the positive x-axis, positive y-axis, and positive z all added together. I guess, yeah, we're dividing. Oh, this is adding the x and the y and the z. I was gonna say it's dividing the z out onto p, but. And then reflect across that if it's less than 0. And this is our sign, not 0 being 1 or -1 for each x and y axis. And it's another ternary, so we either do the flip or we just return it as is. Okay. And so this is our fast version. Is this the precise version here? Or is this, oh, this is decoding. Given a vec2, construct a vec3 out of the xy, and then the z value is the other two values -1. And if our z value was less than 0, then we have to project the xy, or not project, flip the xy axis. Okay, I'm not fully understanding how the octahedral mapping is happening, but this paper isn't really discussing exactly how it works mathematically. It's like I understand the whole flip across the x-axis or z-axis or whatever, but then I'm like, wait, how does this math do that? But in an effort to try to get through the paper, I'm not gonna dwell on it.
Yeah, I think PBRT description is better than this paper on how exactly it happens.
Oh. Okay,
Just the thing we read last week.
I may not have been paying much attention then, but maybe I should review it. So a precise encoding uses a different algorithm. Use the floor operator instead of the round. Oh. Ooh, that's a lot more math. Yeah, that's a lot more expensive. Oh, so it's basically saying, hey, check whether it's better to whether we're should be rounding down or up. You know, if your floating point value is 0.9, you want to round up, not down to 0. I yeah. That is my understanding of what this code is doing. Ooh. Optimal rounding direction for the Y component during float to decimal conversion. At 12 bits per pixel. Black is floor, white is ceiling. So wait. Are these, how detailed is this image? Are these gray at all, or are they just a extremely fine detailed dither pattern?
I think it's showing, I thought it's showing the magnitude of the error. But I don't know. I assume that like 50% gray would be like precise or something, and then white would be off in one direction, black would be off in the other direction. Did they explain like the graphic
Not that.
anywhere?
I mean,
Oh, black equals floor, white equals ceiling.
so they say that. What I'm more asking is this image like a perfect representation of it and it's just been compressed as like a JPEG, not JPEG, but like a PNG? And so it effectively was dithering to get the grayscale values that we're seeing here? Or did they like already average out across, you know, in this, in a certain pixel square, did they mathematically figure out what the average should be? Actually, I don't think it really matters because the image algorithm the image format used is going to compress it no matter what, because we're talking, you know, 4 billion values across, or possibly 4 billion. Or is it just 12 bits per pixel? So it should be like 4,000 values across it. So yeah, maybe it actually could be done by hand. Though 4K image is still pretty large. I'm being distracted. Hacking 24-bit into RGB8. And if we just pack it into the 8x3 SNORM format, we get the same alignment that we want, but we just have to take the G value and cut it up and then give it to the R and B and get our 2x12 format. Okay, some math for going between the two, you know, 8x3 and 12x2. I mean, are they both the slow format? Where does it say oh, this is listing 4. Listing 5 is the optimized one. They are thorough. Yes, so I have all the 16-bit formats here. Uh, and as you add more bits, you get more precise numbers, or you get smaller error. Oh, the list goes on. Because it has to have all the 24-bit and 32-bit variants. Okay. Wow, these are pretty close together at the end of the day. For their min error, their max error is a bit larger in difference. Ooh. Okay. Oh goodness. A quick lesson in Visual Studio floating point modes. And if you're trying to do computation that's stable between different processors, then you're going to want strict. And I can see that being relevant if you're doing, I don't know, a networked multiplayer game where you have to predict things and the numbers have to agree over time and can't just diverge. Not without your server having to rebroadcast everything every once in a while, update every one of the actual numbers.
It's funny that I think game dev is like the most proponent of fat math is a good thing, because everyone else was like, well, that's horrible, but game dev, I've seen game dev said like they use fast math for all the projects they compile.
Yeah. I mean, maybe fast math is worth it, except your numerical stability, might not be reliable. And maybe fast math is the source of a lot of fun bugs in our, gaming lives. When things go weird and there's not really a reason for it, it's because the math broke down. Why did the math break down? I don't know. But SSE and AVX exist and make things more complicated, so we're not going to consider them, at least for performance comparisons. I'm not gonna go too deep in their performance timing just because there is so much you can do to analyze performance of algorithms. And you could probably nitpick it 10 ways to Sunday, but I'm gonna assume it's a best effort, reasonable method to do the comparisons, because it's all CPU off as well. It's not comparing GPU, and it's just the cost of encoding and decoding, not the trying to factor in bandwidth costs as well. But oh, and then GPU stuff. But like the irony is this isn't comparing the bandwidth cost, but these different formats will have different bandwidth costs based on their bit size. So that's interesting. If it's not correct but still looks good, is it incorrect? This is actually a pretty nuanced take, because not take, but in computer graphics, the goal is to try to make something that looks good. And we do a lot of effort to make it look correct, but at the end of the day, looking good is a subjective thing. However, if you don't try to be correct, you get all sorts of fun issues with aliasing and bugs creeping in due to the incorrectness of implementation that will make it look qualitatively worse. So it's not strictly only a qualitative difference when you are considering it mathematically from like signals perspective. Yeah, a bumpy surface with lots of air is going to look worse than a smooth surface. Where are these are these just the dots that, oh, these are just comparing the distribution. Which, interestingly, a perfect distribution would look like a Fresnel lens or for Fresnel pattern, because it'd be bunched up at the edge, because when we're looking at it side on, it's going to be, you know, more dense on the edge. You can see some wacky distribution in various things, like with the octahedral, you see here slightly bunched up in the octant corners, but lat long and the poles, it's bunched up. Equidistant has some interesting double cover, it almost looks like. Oh God, why is this so much blacker? Is this because it's, I don't know. Oh, these are all 16-bit and this is 24-bit. So there is 3 times as many dots on this. They form nice moire patterns. Cool. Comparison. Yeah. So the darker regions have lower air, except if you're looking at the edge of the sphere where you're not looking at it straight on and you're just looking, you know, like here, the octahedral, you can see the poles are bunched up here, but that's the pole. Side on, okay. I really like this visualization. This makes this paper stand out to me, especially this. That is, ooh, so smooth. Is zoom compression making the dots appear?
It looks all right.
Okay, yeah. Okay, get some pretty pictures. Oh. Very subtle difference between the 2 images, only on the edges of shapes, really. I can see banding here. And that's showing up as air, same here on this surface, but it's not appearing here. Oh, and there's some along the, okay, yeah. Glossy is much worse than a Lambertian, no surprise. Some close-up differences between the different formats. Our reference, which is this one, nice blended, smooth things. All of the 16-bit ones just are banded to different love degrees. Even our 24-bit one here is still banded somewhat. The equal area and ellipse actually kind of looks smooth. Same with octahedral 24 bits. I'm having a hard time quantifying the differences between the images, but I'm just gonna assert that you need at least 24 bits to make it reasonable. 16 bits just is not enough. And if you get to 32, you are possibly overcompensating. But maybe it's worth it for certain use cases. Conclusions, finally. Octahedral wins, and so does spherical. Minimal error, efficient implementations, no tables. Lua programmers are distraught. Um, Ooh, that's not something I've seen happening in the last 10 years. But that would be pretty cool if it was baked into the hardware as like a specific format type. Yeah, if you have quantization error, putting a little noise in it will more or less dither it out into it being mostly imperceptible. I think I keep seeing this mentioned as a solution, but it's interesting to see it as a a theoretical description rather than a. We had issues with banding, so we added noise. It's like, well, here is a theoretical description of the problem, and yeah. Um, if your normal map has mostly low frequency detail, maybe you shouldn't be storing it in low frequency normal map, but you should be using a smaller image size or texture size. But I guess DXN exploits that, so that's fine. Um, but okay. I'm starting to get into skim mode. Oh no, other dimensions. Uh, okay, that's it. Anything else we want to discuss before ending recording? No?
We're good.
Okay.